Alrighty, now we're in business as far as recording is concerned. All right, so again, going back to sharing my screen. All right, so I think this is the third time I'm going to say this. So delta G standard is equal to minus RT ln K, all right? So this is one way of expressing it. Another way of expressing it is RT, sorry. Another way of expressing it would be K is equal to E to the minus delta G standard over RT. So these are two ways of saying the same thing. This you'd use if you want to calculate delta G, and this is what you'd use if you want to calculate K. So for example, in this question, it says that methyl alcohol has a delta G formation of minus 166.27 kilojoules per mole, and it gives the equation, and the question is asking for you to calculate Kc. So I would use this form right here. So Kc in this case would be equal to E to the minus delta G, which is this right here. So that's minus 1.6, I'm sorry, 166.27. 166.27, and this would be kilojoules per mole, divided by R. Now, the R that you're going to use in this case is 8.31 joules per mole Kelvin, right? Multiplied by T, which is the temperature, which is 25 degrees Celsius, which is the same thing as 298 Kelvin. Now, again, you have to make sure that the units will work out, because here we have kilojoules and here we have joules. So what I would do is continue to multiply this by 1,000 joules below and 1 kilojoules above. So what's going to happen is that this kilojoule unit will cancel out. You know what? I made a mistake. So this should be the other way around. You know, you have to be careful when doing this because you're dividing by RT. Okay, you know what I'm going to do to avoid confusion? I'm going to do the unit conversion first. So I'm going to convert the kilojoules to joules. So 1 kilojoule down here, 1,000 joules above. And then I'm going to divide all of that by RT, 8.31 joules per mole Kelvin times the temperature, which is 298 Kelvin. Okay, so what's going to happen here is that the kilojoule unit here and here will cancel out, the joule unit here and here will cancel out, and the mole unit here and here will cancel out, and the Kelvin unit will cancel out. So there'll be no units associated with this part right here. And I think I did this math already, and according to my calculation, this works out to be equal to that's not it. This works out to be equal to E to the 67.1, which works out to 1 times 10 to the 29, according to my calculation, which I did. All right? So that's basically how that is done. And let me just say this, and I think I stressed this when I was discussing this topic in the video. There's a sort of inverse relationship between the free energy and the equilibrium constant, primarily due to this negative sign right here, right? So basically, if you have a situation where K is large, if K is large, that means that delta G would be large and negative, all right? If K is small, that means that ln K would be negative, which means that delta G would be positive, right? So that's the kind of relationship between delta G and K. So basically what we can say is that any reaction with a large equilibrium constant, its delta G is going to be negative. In other words, the reaction will be favorable, because remember, delta G is basically what we use to make predictions as to whether or not a reaction is spontaneous. If delta G is negative, then the reaction is spontaneous. If delta G is positive, then the reaction will be non-spontaneous. Okay, any questions about this one? Any questions about number 6? Any question about number 6? All right, let me clear this and scroll down. Okay, so let's look at number 7. So number 7 says, use the free energy data provided to calculate Kp for this equation right here. So basically what we need to do, again, we're going to use the same equation. Delta G is equal to, delta G standard is equal to minus RT ln K. In this case, K would be Kp, right? So basically, so we're going to use the other form, which is Kp is equal to minus delta G over RT. So it's kind of similar, excepting that we have to figure out what delta G is, and we can do that by going to the table.
Isn't it to the e to the power of that?
E to the, right, thank you, you're right. E to the power of minus delta G over RT. So we need to find delta G first. So that means we have to go to the same table that I talked about earlier, and we have to look up the values of all of these here for delta G. Now, because nitrogen and oxygen are elements uncombined with anything, and they exist as they are in nature, this would have a value of 0, and this would have a value of 0. So what we have to do now is look up the value for, okay, what's going on with this thing here? What did I do? All right, so what we have to do now is look up in the table for the value for nitrogen monoxide. So let me come over here and look up the value for delta G, standard for NO. And according to this here, that is equal to 86.55. 86.55. But we have to be careful because we have to recognize that because there's a coefficient of 2 here, we have to multiply that by 2, right? So delta G standard is basically going to be equal to 2 times 86.55 kilojoules per mole minus 0 plus 0. And according to my calculations, this works out to be equal to 86.55 times 2, 173.1 is what I got for that, right? So 173.1 kilojoules per mole. And then we plug that into this equation here. So Kp would be equal to E to the minus 173.1 kilojoules per mole divided by 8.31. Oh, by the way, let me do the conversion again. So let me convert kilojoules to joules. So we're going to have 1 kilojoule here, 1,000 joules above, and then divide by 8.31 joules per mole Kelvin times the temperature, which is again 219 Kelvin, right? So again, the kilojoule units will cancel out, the joules will cancel out, the moles will cancel out, and the Kelvin units will cancel out. So when I did this calculation, I got E to the minus 69.9, which works out to be equal to 4 times 10 to the minus 31.
How does sig figs work for E?
Okay, so I'm trying to remember if I told you guys this, but whenever you're finding the log of a number, whatever the number of sig figs in that number,
How many is it?
Is it how many decimal places, so it's a reverse.
Sorry.
Right, so that's why
Yeah.
we have one decimal place here. That means there's one sig fig here,
Yeah, I get it, that makes sense.
all right? Okay, any other questions about this one? Any other questions? Any other questions? Okay, let me clear this. Or maybe I should, because I think I'm gonna need the answer. Hold on, let me see here. Assume that delta H, anyway, all right, I'll just go ahead. So it says, assume that delta H and delta S are nearly constant with temperature. Calculate delta G at 700 degrees. Estimate the Kp from the new value of delta G reaction, all right? So what they're saying is that we assume that delta H and delta S would be the same at 700 degrees as it would be at 25 degrees Celsius. So what I would do is, well, let me just rewrite the equation here and squeeze it. By the way, I hate this color, so let me change it. Okay, so the equation for the reaction is, of course, N2 gas plus O2 gas to give 2NO gas, right? Okay, so the first thing I would do is try to find delta G standard, which would be equal to delta H standard minus T delta S standard, right? So I need to find delta H for the reaction first. And that would mean that I have to go to the tables. I did that already, so let me just, in the interest of time, just show you what I got. So delta H would be the total enthalpy of the products, which would be 2 times 90.25 kilojoules per mole. All right. So this value here I got from the table for NO, right? Minus, of course, 0 plus 0 for both the oxygen and nitrogen. And when I worked that out, I got 180.5 kilojoules per mole, right? And then I do a similar calculation for delta S standard. That would be equal to 2 times 210. This is the value that I got from the tables again, 0.76 joules per mole Kelvin, minus the sum of the entropy of both nitrogen and oxygen, which from the tables I got 191.6 kilojoules, not kilojoules, what am I saying? Joules per mole Kelvin. 191.6 joules per mole Kelvin plus 205.14, same units, joules per mole Kelvin. So when I work this out, I got the final, well, not the final answer, but the answer for the entropy of the reaction is 24.77 joules per mole Kelvin. All right. So now that we have delta S and delta H, we can plug those values into this equation. So let me just create some space right here to find delta G standard. And delta G standard would be equal to delta H, which we calculated to be 180.5 kilojoules, minus T, which is 298 Kelvin, times delta S, which is 24.77 joules per mole Kelvin. And what I would do here is convert that to kilojoules per mole Kelvin. So 1 kilojoule here above and 1,000 joules below. And then when I did that calculation, I got, oh, wait a minute, no, big mistake. The temperature is not 25 degrees. The temperature is 700 degrees. So 700 plus 273 give you what? 973. So please change this here to 973 Kelvin. 973 Kelvin, right? Okay, so when I did that calculation, I got 156.4 kilojoules per mole. And that's how that is done. Now, we're not finished yet because the question is asking for the KP from the new delta G value that we got here. So let me just erase this part right here. So KP is equal to E to the minus delta G standard over RT. So that will be equal to E to the minus 156.4 kilojoules per mole, which I'm going to convert to joules. So 1 kilojoule here, 1,000 joules above. Multiply by, no, sorry, not multiply, divide by R, which is 8.31 joules per mole Kelvin, multiply by the temperature, which is going to be 973 Kelvin. And when I did that calculation, what did I get? I got E to the minus 19.3, which would be equal to 4 times 10 to the minus 9. And that's how that is done. All right. Any questions about this one? Any questions? Any questions?
Okay, good.
Hmm?
When I did the delta S calculation, I got 24.78. I mean, it probably doesn't make that much of a difference, but
Let me see. So if I work out what's within the parentheses first, that'll be 191.6, right? Plus 205.14. And then I subtract from that 2 times 210.76. Yeah, you're right, 24.78. So this will be 24.78. And therefore, how does that change things? I don't think it's going to change things by much. Let me see here. So 973 times 24.78 divided by 1,000.
yeah.
And then I'm going to subtract from that 180.5. Okay, let me do this again. 180.5 minus 973 times 24.78. Okay, so this part here, I got one. It doesn't change things, right? Yeah, one because it works out to 156.4.
Yeah.
Which leads to the same answer. All right. Okay. Any other questions about this one? Any other questions? Any other questions? All right. Let me clear this. And let's see what comes after. Oh, that's it. Oh, shoot. I didn't realize. All right. So what I'm going to do now is set up a Dropbox for this one. So this is assignment number, what is it, 6? No. Assignment number 6. Edit. Okay, so I am going to let this be due. Today's what? Today's the 13th. I'm going to let this be due on the 16th. Let me just do some more stuff here. Okay, so let me. Oops. 16th, okay.
Do you know when test 2 will be finished?
Man, I'm catching up on all the pent up work that I could not print since I did not have access to a printer all this time. So I was hoping to get the test graded by over the weekend, but I just couldn't get to it because I wanted to get out some of the assignments, and I haven't even got to Chem 2 assignments. I was focusing on Chem 1 and intro. I would say, by the end of the week, end of this week latest. I apologize for that because I just couldn't help it. Believe me, I've been working feverishly over the weekend trying to clear the backed up work. Okay, so let me at least get you started on the next topic, which is electrochemistry. And for those of you enrolled in my lab, you have had some introduction to this. And I could probably understand if you're confused about certain things. So what I'm about to discuss should clarify some things that you encountered in the lab. Now, before we get to the actual electrochemistry, we need to be reminded of the terms oxidation and reduction. And this is something that you should have met in your Chem 1 lecture. You certainly would have met it with me. Okay, how do I get this? Display settings. Okay, so we have a broad group of reactions known as electrochemical reactions, right? And these reactions are all redox reactions, right? So just to remind you of what redox reactions are, a redox reaction is where you have one substance transferring electrons to another substance, right? So the substance undergoing oxidation is a substance that is losing electrons, and the substance undergoing reduction is a substance that is gaining electrons, right? Now, what happens in an electrochemical process is one of two things, right? You either have a reaction, a spontaneous reaction, which produces electrical energy, or you have a situation where a reaction which would otherwise be non-spontaneous is actually caused by an electrical energy source providing energy for that reaction, all right? So all electrochemical reactions will fall under either this category or this category, all right? So just to remind ourselves of what happens in a redox reaction, this simple reaction here, the reaction between magnesium and oxygen, is a redox reaction because as you go from magnesium on this side to the magnesium ion on the other side, it is losing electrons. And at the same time, the oxygen is gaining electrons from the magnesium to form the oxide ion, and therefore the magnesium and oxide will come together to form magnesium oxide, right? So of course we know that we can use half reactions or half equations to represent the oxidation part of it and the reduction part of it, right? So, and I remember for those of you who had me in Chem 1, you should recall this, which you can use as a useful tool for remembering what redox is. Oxidation is the loss of electrons, and reduction is the gain of electrons. So, that may help in terms of you remembering what happens in a redox reaction. All right. So, with that said, let me clear this first. And by the way, you can track what is being oxidized and what is being reduced by looking at the changes in the charge of the species involved. So like in this case here, the magnesium on this side has a charge of 0, but over here it's +2, right? So if there's an increase in charge from 0 to +2, that is basically oxidation, because in order for the charge to increase, the magnesium would have to lose electrons. And then on the other hand, the oxygen on this side has a charge of 0, but on this side has a charge of -2. So there is a decrease in the charge, which means that the oxygen is gaining electrons and therefore is undergone reduction, all right? Another term that you would have met in General Chemistry 1 is this term oxidation number. And if you look in different textbooks, you'll see different definitions. So the definition that we have here on the screen is that it's a charge an atom would have in a molecule or an ionic compound if the electrons were completely transferred, all right? And there are some rules for you to determine the oxidation number of an element in a substance, right? And I'm going to go through these rules because you should actually know them already. So I'm going to go through them rather quickly. First rule is that free elements, in other words, elements not combined with anything else, automatically would have an oxidation number of 0, all right? The second rule, oh, and by the way, these are just some examples of elements that are uncombined, and as a result will have an oxidation number of 0. In monatomic ions, the oxidation number will be equal to the charge on the ion, right? So monatomic ion is created from one atom, right? So whatever the charge on the ion, that would be its oxidation number. So we have some examples here. So for example, for the lithium ion, the oxidation number is +1. For the iron 3 ion, the oxidation number is +3. And for the oxide ion, the oxidation number is -2. All right. The next rule has to do with oxygen, right? Now, in the case of oxygen, its oxidation number is usually -2, but there are certain exceptions. And the exceptions would be in the case of hydrogen peroxide or any compound that contains an oxide ion. In those instances, the oxidation number of oxygen will be -1. Otherwise, if oxygen is combined with any other element, then its oxidation number will be -2. All right? So that's a special rule for oxygen. And then we have another rule for hydrogen. Get this out of the way here. So in the case of hydrogen, its oxidation number, if hydrogen is combined with some other element, its oxidation number is usually +1. However, if it's bonded to a metal, right, like sodium or magnesium, then its oxidation number in those situations would be -1, all right? So that's a special rule for hydrogen. The next rule has to do with elements in certain groups. If the element is in group 1A metal, then, and if they're combined with anything else, their oxidation number would be +1, I'm sorry. If you're dealing with group 2 metals, then their oxidation number would be +2. And then there's a special situation in the case of fluorine. If fluorine is bonded to anything, doesn't matter what it is, its oxidation number is going to be -1, all right? And then here's a rule that is used to calculate the oxidation numbers of other elements that were not described earlier. The sum of the oxidation numbers of all atoms in a molecule or ion is equal to the charge on the molecule or ion. So for example, let's say you're given this question. What are the oxidation numbers of all the atoms in the case of the bicarbonate ion, HCO3-, right? Well, we know from an earlier rule, in fact, rule number 4 here, that the oxidation number of hydrogen is +1, right? And we know from rule number 3, I believe, the oxidation number of oxygen is -2. So this begs the question, what is the oxidation number of carbon? Well, in order for us to answer that, we have to use rule number 6. Rule number 6 says the sum of the oxidation numbers of all the atoms in a molecular ion is equal to the charge on the molecular ion. So therefore, based on the fact that hydrogen is +1 and oxygen is -2, and there are 3 of them, we can calculate the oxidation of carbon because the sum of all the oxidation numbers of the different elements in this ion would be equal to the charge, which in this case is -1. So therefore, we can set up a simple equation. Oxygen is -2, hydrogen is +1, carbon is what we don't know. So basically, it's 3 times -2 for the oxygen because there are 3 of them. We add that to 1 + 1 for the hydrogen, and the unknown would be the oxidation number of carbon, right? So the sum of all of these would be equal to the charge, which is -1, which means that we can solve by using simple algebra to find the oxidation number of carbon, which would be +4. So that rule is useful for determining the oxidation numbers of elements that were not described in the previous 5 rules. Okay. Another thing that we covered, again, if you had me in Chem 1, is how do we go about balancing redox equations? And I remember saying to my Chem 1 students last semester that you can balance redox equations in the normal traditional way, but in a lot of cases, that will be very difficult, very complex. So therefore, there's another method. In some textbooks, they call it the electron ion method. And I'm just going to go through this to remind you of what is involved in this method. So let's say you're asked to write down the balanced equation for this reaction. And let me just say from the outset that this is not enough information, because what you're gonna need is what would be the product when this is reduced. So let me just add a little information here. Let me put it here. Oops. Producing chromium 3+, all right? Okay, so how would you go about balancing this equation? Let me see if my students from Chem 1 can remember the steps. So what would be the first step in this process?
You gotta make your two separate equations.
Okay, so
Like one would be Fe 2+ equals to Fe 3+.
exactly.
And the other one would be CR.
Fe 2+ to Fe 3+, and the other would be Cr2O7 2- to Cr 3+. All right, so basically you're writing down the two half equations. What's the next step?
You have to balance out the oxygens for
Oh, You're
no.
gonna do that later, but there's something, you just missed a step or you just jumped over a step. Can anybody out there in Zoom help him out?
Is it the charges or no?
No, not the charges, that's later on, that's later on.
Well, usually you have like hydrogen involved, but
That's later on as well.
so I guess I don't know. I don't know then.
Anybody out there in Zoom can help him out? What would be the next step? Once you have the two half equation, what's the next step? Let me see.
You have to balance. You have to balance Fe and Cr.
Do I need to call some
First.
people out? Let me see who is there that was in my class last semester. I don't remember, was Mr. David there? I know the Afrin, oh, let me see, somebody saying something. Balance what? Okay, Afra is saying balancing something, but what do we need to balance? You're right, we need to balance something. I will say that much. Okay, let me see what this person is. Oh, 3 persons. Balance the chromium. Who said that? Okay, so Mr. David and Miss Anwar, you're both correct. You balance the chromium, right? How do we balance the chromium in this case? Well, because you have a 2 here, you put a 2 here, all right? The irons, you don't need to do anything because it's already balanced, all right? Okay, very good. What's the next step? After balancing, so therefore in this step, you're balancing all atoms excepting oxygen and hydrogen, right? So once you have done that, what's the next step?
Now you can balance out the oxygens, right?
Okay, we balance the oxygen by doing what?
Yeah. What is be adding water?
Adding water, exactly. So in the case of the first half equation, we don't need to add any water because there's no oxygen.
Wait, for the second one, would you have to do plus 7 H2O?
Exactly, on the right side, 7, where did that reading come from?
And then on the other side, you have to add plus 14 H plus.
Oh, 1 minute, let me change the color.
I got you.
How do I change the color? Anyway, all right. But you're right about adding the water. To balance the water, just to remind those of you who might forget, to balance the oxygen, I should say, you add water. So you have 7 oxygens here, and you add 7 water molecules on the right side. The next step is what you just said, which is
Balancing out the hydrogens.
you balance the hydrogens by what?
You had to add 14 H plus.
Exactly, you balance the hydrogen by adding H+, and in this case, because you have 14 hydrogens here on the right side, you're going to add 14 hydrogen ions on the left side. Again, you don't need to do anything here because there's no hydrogens in the first equation. Okay, what's the next step? And this is where, let me warn you, as I warned you last time, this is where students tend to screw up things, all right? What's the next step?
Is charges.
You balance the charges by?
You add electrons.
Okay, so to which side? Okay, let's start off with this equation here. To which side would you add electrons and how many would you add?
You would add it to the right side because it's the greater charge.
Okay, so how many electrons would you add to the right side?
You just add 1.
Add 1, exactly. So 1 electron on the right side. What about the second half equation? To which side would you add electrons and how many would you add? Well, we have to count up the charges, right?
Yeah,
So how many charges do we have total on this side?
that's plus 12.
Plus 12. No, yeah, you're right, plus 12. All right, how many charges total do we have on this side?
Is that one just, is it 6 plus?
Plus 6.
Yeah.
All right. So to which side would you add electrons and how many electrons would you add?
You would have it to the left side and then add 6.
Exactly. So you'd add 6 electrons to the left side. All right, very good. So now that we have balanced atoms and oxygens and hydrogens and charges, let me just erase this here. What's the next step?
This is the step where you have to balance, like you have to multiply, because like one has one electron and the other one has six, so you have to times the other one by like six. to
Exactly.
Balance it out.
Right, so the next step is where you ensure that the number of electrons lost and gained is the same, right? And that is true for every redox reaction. For every redox reaction, the number of electrons lost must be equal to the number of electrons gained, right? So as he correctly said, because you have one electron here and you have 6 electrons here, you would multiply this equation by 6. So you're going to end up with 6 Fe2 plus to form 6 Fe3 plus, all right? Plus 6 electrons, okay? So the next step would be what? After making sure that the number of electrons lost and gained are the same, what would be the next step?
You can cancel out the electrons too, correct?
What's that?
You can cancel them out.
Yeah, exactly. So you're going to add both equations together. And when you're adding equations together, of course, we know that you cancel out those items that are common to both sides, which in this case would be the electrons. In some instances, you'd have to cancel out hydrogen ions and water molecules, right? Not in this case, however, right? And then we write down what is left, which is 14H plus Cr2O7 2 minus plus 6 Fe2 plus to give on the right side 2 Cr3 plus 7 H2O plus 6 Fe3 plus. And that should be the final answer. However, I always tell my students, check to make sure everything balances out in the final answer, right? Check all the hydrogens, check all the oxygens, check all the atoms, and also the charges, right? Because remember, the total charges on the left must be equal to the total charges on the right. So in the case of, let's look at the hydrogens. How many hydrogens do we have on the left? 14, and we have 14 here. So the hydrogens are okay. What about the chromiums? We have 2 chromium atoms here, 2 chromium atoms, so the chromiums are okay. What about the oxygens? We have 7 oxygen atoms here, and this 7 multiply the oxygens here, so you have 7 oxygens on both sides. And then we have the iron. We have 6 irons here, 6 irons here, so the ions are balanced, and then we have to look at the charges. So basically, the total charge on this side would be plus 14, minus 2, minus 6 times plus 2, that's, plus 12, not minus, plus 12. So it's 14 minus 2 plus 12, so that's
24.
24, right? And then on this side, we have plus 6, plus water has no charge, plus 6 3 is 18. So that's what? 24 as well. So the charges are balanced as well. So therefore, the equation is balanced. All right? Okay, any question about this? Any question about this example, right? All right, so let me see here. Let me, so this is just going through the steps that we just did. I'll just skip all that. Okay, I'm going to stop here. What I'm going to do is I'm going to publish the videos. I'm going to publish the videos for you to watch. Let me see here. Let me go here and go to modules and go to, let me see what's here. Okay, so let me publish the electrochemistry chapter now. So I want you to watch these videos. Oh, and there's okay. I want you to watch these videos and then we'll do some problems. All right. Okay, so that's it for today. I'll see you guys next week. Same time, same place. Okay, oh, somebody said something out there in Zoom. That he said I'm supposed to come in. Oh, okay, yeah, no problem, actually. When do you want to, oh, let me see here. Today's what? Today's Monday, Tuesday, Wednesday. What lab are you guys trying to make up? Oh, the buffer lab, all right, let me think. All right, tell you what, I'm not sure about Wednesday. So I would say Friday. Friday at, I'll be here from, well, I can be here in the morning. Oh, I would say 9:30, but you need to remind me. All right, so Friday in the morning, I would say 9 o'clock. All right? Okay, all right. I'll see you then.